God gave us life for a reason. I always tell my kids that.
All right. I lost my clicker.
Mr. Edmund giving us our homework for the white remote.
No, it's the other one. Anyone see my I don't think I have. Oh yeah, good job, Ali. Nice job.
Extra credit.
Or not. All right. So today and over the next couple classes, what we're going to do is talk about nuclear energy and uses of nuclear energy. So today we're going to talk about one type of way to harness nuclear energy, and that's called fission. And so nuclear fission is when large, unstable elements are used. They are broken into smaller components, but in the process, they release huge amounts of energy that can be used. So fission means to split. Nuclear means to split what? The nucleus. To split the nucleus. So if you shoot a neutron at the nucleus of a uranium-235 atom, the nucleus will become unstable and it will break down into barium and krypton. But that process of breaking down this large, unstable nucleus into these smaller nuclei releases energy and particles. And what can be done with this energy? Colin?
Like making weapons out of it.
Could be used to make weapons, or it could also be used for what other purpose? Colin?
To like power stuff.
Yeah, to make energy. What do we call that?
Nuclear energy.
Nuclear, yeah, nuclear power plant. Hello? Hi. So, this energy can be harnessed. Ooh, that wasn't what I was looking for. Oh, we're back in the beginning. So oh no, we're not. We're back here. So the equation that shows this is listed here at the bottom.
Is that like a Wii remote? We used to be all day, every day. Bro, Wii Sports was my life. Oh,
For like an hour.
I was the best player.
So you take uranium-235, bombard it with a neutron, and it breaks down into barium-141 plus krypton-92 plus 3 more neutrons. Now, what do you notice about the atomic masses and the atomic numbers? Colin?
They're not just like +1 and +0. They're like way different.
Yes, but what do they balance out?
I don't know.
Yes.
Yeah, if you add all of the atomic numbers, add up all the atomic masses, they balance out because matter is being conserved here. You end up with the same end components that you do in the beginning. But there's a release of energy in the process. I'm sure you guys have seen this equation before. Who came up with this? Einstein. Okay? And this comes from Einstein's theory of relativity. And it's really not very complicated of a formula. The E part means energy. M is mass, C is a constant, it's the speed of light squared. And so what this equation really tells us, that we can take a very small amount of matter and we can actually convert it into energy. And in this process, a small amount of the conversion of matter to energy releases huge amounts of energy.
Oh, that's the,
And this can happen, we can do this in a controlled manner, okay, in nuclear power plants. If we can take, and you'll notice here, one of the products of the decay of uranium is our neutrons. And so when these neutrons are released, if they hit another atom of uranium, what can happen? That one decays. And what does it release? More neutrons, which can hit more uranium atoms, which can continue this process, which is what a chain reaction is. It's a series of reactions that are sort of self-sustaining. If you have a critical mass of fuel, okay, then this chain reaction can occur. And this is an example of that, this mousetrap chain reaction video.
Spartan candle. Solo, guys.
So one ping pong ball triggers the next. But if we have a large enough number of these ping pong balls, and then it creates this chain reaction because the product from one generates more ping pong balls, which trip more mouse traps, which continues that process until all of them have been triggered. Now, if we just had 2 mouse traps in there, would this necessarily happen? No, because the first one might not interact with the second, and the reaction would not take place. So you need a certain number. We call that the critical mass.
Wait, can you go back?
Yeah.
And in nuclear power plants, we can take this principle and control it and harness the energy to actually produce electricity. I guess we're going to have to talk about nuclear power tomorrow. We'll talk about nuclear energy. Drew.
Alright, here's just the idea. So, if a square and each right triangle is like 90 degrees, and overall it would be 360 degrees, and the circle is 360 degrees, does that mean circles equals square?
Sure.
Alright,
I'm going to go with yes.
Well, you kept that.
It's not as good as Zeno's paradox, but.